Góðan daginn, gott fólk. Klukkan orðin 12:30. Við erum að fara að byrja. Gaman að sjá svona marga inn í salnum í dag og gaman að sjá svona marga sem eru koma annar stað frá, langt í burtu. En fyrirlesturinn okkar í dag heitir Hjálmar Hátún. Hann er nágranni, vinur og frændi hérna frá Færeyjum. Hann er haffræðingur, búinn að vinna við þetta í 25 ár og hann sér sig í því að skoða svona, við vorum að tala um þetta áðan alltaf á ensku, nú er hérna þýðið yfir íslensku, gengur frekar hægt, svona stóra hafstrauma sem ná yfir stór svæði. Velkomin Unnur. Og hann ætlar sem í dag að vera með yfirlitsfyrirlestur þessa stóru hafstrauma og þessar stóru sveiflur í þeim í norðaustur-Atlantshafinu og hvernig breytingar í hafstraumunum fara svo í gegnum allt lífríkið, hafa áhrif á frumframleiðni, átu, fiska og jafnvel á hvali. Þannig að þetta er svona yfirlitsfyrirlestur þar sem við erum talað margt og hann ætlar meira að byrja fyrirlesturinn sinni á því að tala AMOC, en áður en ég hleypi honum á salinn þá verð ég að segja ykkur það að þessi fyrirlestur er tekin upp og sýndur á YouTube, þannig að ef það er einhver á móti því þá verður að rétta upp hendi, ég ætla hann að viti af því. Allt sem ég segi verður tekið upp. Ég lofaði henni Dóru samskiptastjóra að segja þetta. Þannig að nú er ég búin að koma sem vel til skila, eigum þá ekki bara að hleypa Hjálmari í púltið. Gerðu svo vel Hjálmar.
Já, púltinn hér.
Já, ok, hann ætlar að vera þarna. Gerðu svo vel.
This did not work, so I'll just speak up loud and I hope people on the internet can understand or hear me. And I got most of what you said. It's nice to be here. I love to be in Iceland. Cold and warm pools and all these things. I enjoy it a lot. Yeah, so what to talk about? I think I'll go about 35 minutes and then we can discuss afterwards. I was kind of lost. I was here 2 weeks ago. We have to touch upon this AMOC stuff. It's, as you know, it's a warm topic, so might be maybe a bit provocative, but say what we do in the Faroes on this AMOC, the Atlantic Meridional Overturning Circulation. We measure it in the Faroes, and some discussion on, let's not go too far in this AMOC, let's be moderate. Talk about convection and some about predictability, go to the subpolar gyre, and then some snippets, some short stories just around this subpolar gyre to ecosystems. Here you see the Atlantic inflows, warm Atlantic water that goes your way and our way, and they pass across this Greenland-Scotland ridge. So if you look down on this ridge, you see Iceland, the GS ridge here. The inflow, warm Atlantic water, they're coming in, they're warm near the surface, and parts of them, they go through the East Greenland current in the surface, partly also towards the Faroes again in the East Icelandic current. But these warm waters, they give a lot of heat to the atmosphere, so they're cooled. They're colder and they're denser and they tend to sink down into the space north of this ridge. And when it's full, it flows over this ridge, an overflow. And that's the overturning circulation, it turns over. These waters, when they come over this ridge, they do so through the Fairbank Channel, this Iceland-Faroe Ridge, and also Denmark Strait. They come together as North Atlantic deep water. It's the deeper branch of the AMOC that spreads into the world oceans. Let's go a bit closer. Iceland and the Faroes and the Iceland-Faroe Ridge, you see the topography here. And if you put colors onto it according to the water masses, we have the warm Atlantic waters here that go towards Iceland and meet the East Icelandic water. And there's a front building up here, and then continue towards Norway. This is the Iceland-Faroe front. And south of that, we have this Faroe current. I actually wrote my postdoc on this Faroe current. Parts go towards Norway directly, parts go into this Faroe Ocean Channel, and they meet this boundary current that goes towards the high Arctic. And also some parts of these waters, this is East Icelandic water, they slide underneath as modified East Icelandic water. And the unique part or thing here is that this sluggish large AMOC system, it goes through relatively narrow currents which are observable. that's what we do here in Faroes. So we, like you do, we measure them at along standard sections with our ship. This is our new research vessel here. And then we go out, do these CTD casts down. And then we measure these subarctic waters. That's the gift from Iceland. They come from the East Icelandic current towards us. And this is the Atlantic inflow, these Atlantic waters. And we do also have current meters, like here, moored down underneath, and then they measure with acoustics. Then we get the flow field, and when we get the flow field, we can calculate how much water is flowing through it. Then we also get temperatures, for example, and salinities in the Atlantic waters. We also use satellite data, should be said. They measure the curvature of the sea surface, which relates to currents. And then we follow what are changes in temperatures and salinities in this Atlantic inflow. For example, as shown here, for the Faroe Channel, you see it's been warming a bit and a bit cooling again in recent years. It's a bit warmer, it's not quite updated. And this is the Faroe current, and they do about the same. So warming through the 90s and a slight cooling. Levels are about what they were. So it's not a strong signature yet of warming. Salinities, they show more life. This resembles the Sopolar gyre, which we've come to. We had this weakening of the gyre through the late 90s and into the 2000s. It became saltier and saltier, and then suddenly after 2015-16, we had a major drop in salinity. This is the strongest great salinity anomaly that we have observed after 2015, and it's been kind of climbing up again. So much fresher here, which could have an impact on the AMOC, because fresh is light. We want density, we want dense water to kind of press this AMOC system. And with the HSPs, the current field, and also measuring temperatures, we can say how much goes, for example, through this current of waters that are Atlantic, that are warmer than 4 degrees. And this is, given the Sverdrups, it's 1 million cubic meters per second. That's the unit oceanographers use to measure. So it's a kind of pulse going all the time, fairly steady, not declining yet, about 4 million cubic meters per second through this branch here. So no sign of a weakening here yet. And if we multiply the currents by temperature, then we get heat transports given in watts, how many watts or terawatts are blown towards the high Arctic. And this is really the critical metric, how much heat is going towards the Arctic or into the Nordic seas. And actually it's a slight increase because they do become a bit warmer, the waters. And then the other way, they don't get the sound, don't get the sound on the internet, right?
It was a question if asking people on
they
say it's good.
It's good, okay, nice. Yeah. And then we look through this, that is the Faroe Bank Channel overflow. It's a massive waterfall that goes over there. It's about twice the amount of all rivers in the world. Just over 2 Sverdrups, just flowing all the time through there. Fairly steady. But if you look at the temperatures down in this overflow, they have risen. They have been rising through the last good 20 years of about 0.25 degrees. And when they become warmer, they become lighter. So this could have potentially impact on the AMOC as well. Now to maybe more philosophical or maybe a bit provocational, you've heard about this. I mean, you hear about the Gulf Stream is kind of dying several times a year now, so this has really been headlines. And then we hear it's going to be much colder, it's going to be much warmer. People are kind of confused about this. So let's discuss it a bit. This image went viral in the world media view in 2015. It shows temperature on Earth. It was an El Nino year. The world was really warm, except this blue or cold blob there. And since this resembles the long-term projection of climate models from the IPCC 100 years from now, they said, oh, it's almost, or maybe it's happening. And then the drama was on in the world media. Yeah. Then this metric, in order to say what has happened to this overturning, they go to proxies, not direct measurements because they're few and short, but proxies for the AMOC. And it really started with this one, a paper in Nature by Ramsdorff, who has been really proactive in this, professor in Germany. They say, oh, let's just assume that the AMOC can be proxied by SST, means the sea surface temperature, or the subpolar gyre, minus the global temperature. The rationale being that if this stays colder than the rest of the world, this means that there's less heat influx to the system. That means the AMOC will be weakening. But that's a really rough metric. And for these temperatures, they use 3 rings or from an FRA or some proxy records to say something about this. And this is a highly doubtful proxy, but that's what they use. You could say, what is the global temperature? Something like this, it's been warming, right? And if you subtract this, then we will see a signal that goes like this. And also, when it's really cold, there is not just lateral transports of heat, it's also air-sea cooling. When you have really cold, strong winters, that means that the subpolar gyre is colder. That's actually more overturning. So this came out in his paper in 2015 in Nature. And many others have then used this to just assume that this metric is the correct one. A recent paper, a Danish one, it was, they just start from here and use statistics and say that the AMOC will stop in the year 2037 or something like that. Huh? And then the media goes viral again. This is a sensitive topic because we should follow it, of course, but we should not over-dramatize, because this metric is probably not valid. That means that the basis of many papers that go into Nature at the onset is not valid. So what do we need to do? I mean, we need to, of course, go out there and say, let's reduce the CO2 emissions, but I think we all here agree, and most people agree, we should get CO2 emissions down for many reasons in the world, also the AMOC. But how much should we dramatize in order to get the attention of media and people? What's our role? Are we activists or scientists? It's a quite involved philosophical or ethical question. And we have to step back because we all have opinion about this AMOC, but is it well defined, you could ask? If you ask different people, they have different answers. So it's a kind of a blurred concept in itself. It's a metaphor. Is it a conveyor? The idea came from Brøker back in the 80s that you have this conveyor, like when you have the luggage in the airport and you put your luggage there, and after a while it will come there. It's connected along this conveyor. I'm just asking these questions now. I think it's good to just think about them. Do we have long-term direct observations of the AMOC? And if yes, do they show decline? And from these records of the AMOC, do they resemble something in the ecosystems? I mean, can we use them to inform us about our resources in the oceans? And then when we go to proxies to get longer time series, are they, I mean, 3 rings from the NEFRA, are they reliable? And it's also the danger of, I mean, you want to stay in business or you want to see your face on Nature and so on. I could be used for self-promotion. You just have to, I know this is a bit provocative, but it's okay. And then, I mean, you should retain this AMOC concept because it is a kind of a metaphor. Should we continue to monitor it? And I would say to the first one, it's not quite clear. I mean, you get different answers if you do ask different people. And even the connectivity between, if you have sections further south in the Atlantic, do you see first a signal further south in the Atlantic and then you see further north? That's also kind of doubtful, and then the basis of the concept shakes a bit. Do we have long-term records? We do some. We have some in the Faroes and the Florida Straits, they have some, so yeah. Do these show a decline? No. Although many claim they do, there are no declines observed yet. And these records, we have some of the longest ones, and they do not resemble seabirds or fish or something. They're kind of steady, so you cannot use it directly to inform something about fish stocks. The longer proxy records are doubtful, and I'm not saying that people, I mean, they have good intentions, I'm sure, but there is a little danger in this one. So should we then retain this concept? Yes, it is important. I mean, we need a metaphor to explain something really complex, and it does the job. Just these metaphors can be overused. It's just the danger of overuse. So we should retain it, and yes, indeed, we should monitor it. It is still a very fundamental aspect of the marine climate in the North Atlantic, and the IPCC expects this to decline about between 0 and 50% the next 100 years. And just if it declines just a bit, it is really serious for Iceland and the Faroes. So we should absolutely keep a finger on the pulse. But this drama about collapses and so on, we should tone that down because it does not serve a purpose. And people get kind of confused in the media, they get scared, apathetic, and so on. So I think it's important to find the right balance of communication. And also, very often, when people hear that I'm an oceanographer, oh, the AMOC, everything goes in that. So almost oceanography becomes synonymous with the AMOC. And there's so much else that we also should measure. I mean, local processes, lateral gyres, that do actually reflect regional marine climate around Iceland or the Faroes, where we have long observational records and where those records actually do resemble things in the ecosystem, which therefore could be used to inform management of our resources. So we should keep this, but this should not overshadow everything else. Does it make sense? I'm too provoked. Yeah. So the message is that we do have a solid monitoring program for this in the Faroes. There's no weakening, maybe a bit strengthening, although they are becoming warmer. This could, in the future, have an impact. We saw this massive freshening after 2015, and we have not seen that yet. You could imagine that if it becomes much fresher, it becomes lighter, and that could also slow down the AMOC. So the last point here is actually because something happened now just recently. Ramsford went out and got lots of signatures on a few-page paper to the Nordic ministers. So I think that's a quite brave thing to come into our Nordic ministers, collect all these signatures without saying all those people that did not sign. Maybe there are many people that did not sign this paper. So somehow I think Nordic countries should try to lean and moderate this discussion. This is the first part. Then we go to convection and these lateral gyres. This convection, yeah, it's due to the jet streams that pass us. They cool the oceans and they are mixing deep down in winter time. This mixing brings up lots of nutrients to the sun that gives primary production. And we have some of the greatest production in the open oceans in the world. So we are blessed with very productive, especially around Iceland. And this cold blob, it can actually introduce predictability, which is also important to try to, can we predict anything here, to inform management. At that time, it was, oh, this is really bad for the ecosystems, but we claimed that it could be good for some ecosystems when we have expanding gyre and more convection. let's look a bit more at convection. This is Greenland and Newfoundland. Here they have this section across the Labrador Sea. This is so-called Hátún diagram. From here, temperature, and along the y-axis is depth, and out here are the years. And then some years we have massive heat losses. Lots of heat just goes out of the Labrador Sea, like in the 50s, and the convection down. You see how it fills into the gyre itself. Mid-70s, especially in the 90s, lots of convection. And again, after 15, this was the cold blob. It was convection started again. And for example, if you look at the sea surface temperature trend, which they use as a proxy, it goes up and down. It's not going to be easy to find that trend, and there's not enough data back here to really show that. And also they claim that in this period, because SSTs here went down, they would say it was a weakened AMOC. I mean, it's totally opposite. It was really massive heat losses and more convection, more overturning, so a stronger AMOC. So in my mind, it turns the other way around. Definitely not a weakening AMOC here.
Okay, sorry, can you say that again?
Yeah, they claim that because it's colder, SST, it's colder, or the gyre, according to their metric, they would say into the 90s, the AMOC weakened because this area became colder. But that's when you think laterally, heat comes from the sides. But by far, most of the heat exchange is to the atmosphere. And if you look at the seasonal image, this is from Igor Hjálmar from Bedford and Halifax, we see the winters here. Some winters, it breaks through, it comes deep down, 14, and then after here, it starts again to produce, this is Labrador Sea water. And I think we see that when these winters of deep convection occur, in the Faroes at least, I think also in South Iceland, you see increased biological production. There are some years, really, these spikes that go through with increased convection. And these tend to invigorate some ecosystems. It's more breaking up of nutrients, for example. And also that brings in predictability, because if you cool here, this involves a deep water column, down to maybe 2,000 meters, so there's lots of memory, thermal inertia. So when you really a cold winter, all this water column becomes a bit colder. And there's memory in the system because you have the inertia. And people, they love to do that. This is a US, these predictability systems, memory models brought together. And they say, okay, if we initialize our system and then look 10.5 months down the line, you see when it's really deep red, it's high skill score, it's more predictability. Yeah. And the ENSO system, there's some predictability, but if you look close to you guys, if you have a winter with really deep convection, you produce these water masses that actually flow towards Iceland into the Erindi Sea, and that's where you get a part of your predictability. So actually, it's amongst the highest predictability potentials in the world, Iceland and the Faroes. So that's a potential we should utilize. Yeah, and then let's go to this, the gyre. So we have convection here. These waters, Labrador Sea water, produced, and they slide into the Erindi Sea, Iceland Basin, and eastwards, and they are filling up this subpolar gyre. It's a big body of cold and subarctic waters that revolve counterclockwise, and it lays north of the Gulf Stream and the subtropical gyre. Some years back, we showed that the marine climate here south of Iceland and close to the Faroes is governed by dynamics of these two gyre systems. When this one is large, as shown here, salinities are low, temperatures are low, it's quite a subarctic But like in the 90s, suddenly it weakened due to weakening convection, opened up this window, and then these waters had more free passage northwards. And in the 15 again, it became colder again. So this shift between the gyres really regulates the marine climate here. And also downstream, north of Iceland towards the Labrador Sea and further towards the high Arctic and coming down. So also this lateral connectivity due to advective lag will also introduce some predictability, which we together with Greenland should also make use of. And then I have just some snippets, I cannot take it all, built on this kind of simplified. This is also a metaphor. The subpolar gyre, just like the AMOC, is also a simplification of a more complex reality. But revolving around this gyre, we have spent some energy the last many years to look how this influences the nutrients, phytoplankton, zooplankton, fish, pelagic fish, benthic fish stocks, seabirds also, and even up to the marine mammals. I'll not show this. So I'll just show snippets of the system. And then produce a gyre index that reflects this type of variability. That's the dashed line here. And I'm sure you all also, or people here, know this record better than I do. The green one is from Faxaflower. The other one is from salinity from Rockall. Point being that in the early 90s, strong jet stream in the atmosphere was really a large subpolar gyre and was cold and fresh. And a few years after, in the mid-90s, there was really big changes there, in the mid-90s. The gyre weakened a lot there, and then south of Iceland, the water masses really changed a lot. And these changes we have been tracing up through the ecosystem, different parts of the ecosystems through the years. And if we prolong this gyre index, then after 15, when the gyre became stronger again, we came back to something resembling this state again. And I would claim this is actually the blue blob. It is not the AMOC weakening, it's the subpolar gyre strength. And then based on this, we predicted, okay, stronger gyre, then some subarctic ecosystems should be boosted. And many of these predictions have been holding true for the Faroes at least. We have seen slight improvements for fish stocks and also seabirds, and there are aspects in ecosystems that are or have improved after 15. And also looking into this part at a parameter called wind stress curve, curvature of the wind field is the red one, wind curve. This is something that we try to get published now and link it to recruitment of one of these pelagic fish stocks, blue whiting. And this last really strong peak was actually predicted. We said it before they saw it in the data. And feel free to stop me. I'll just take, it can be maybe be information overkill when I just go through here. So we've also discussed these changes here, close to the spawning grounds of these two species, blue whiting and mackerel. They are spawning here and then they are swimming north to feed in the summertime. And we have discussed changes in both blue whiting in the mid-90s when it expanded. They shrunk back, so when the gyre became weaker, they expanded. And after 2005 and 6, they started to move into you guys and all the way down to Greenland and back again. So I'm just showing all these things so we could discuss afterwards if you want. So you can select a discussion topic. And then back to the nutrients. You have much more nutrients than we do. Red is lots of nitrate and silicate. And I'd claim this is the more important one because this is the limiting nutrient in the subpolar Atlantic, more so than nitrate. Very often people hear nutrients, just nitrate. I claim this one is more important because this is the one that stops the big blooms of diatoms in the spring bloom. I think, Jan? You think so?
Yes.
Yeah.
Silicate limits the diatoms.
That's right.
Yeah.
And this is the first one to limit the system.
First, yes. There is still nitrate left.
Exactly. There's still nitrate left, and that's key. That's, Jan says this one goes down to limiting first. There's still excess of this in these waters. That is a message not easy to get past because of nitrate is synonymous with nutrients. Down here is more bluish. We do not have so much. So when we have convection, we bring nutrients up. We also get from the Arctic, and that flows towards Iceland. So when the subpolar gyre expands, it also brings the nutrients with it. And in a paper some years ago, where Jon was also part of it, it was actually based mostly on Jon's good data, or your data, and also the Canadian data from Labrador Sea. And this is pre-bloom, it's a winter silicate, so it's before the bloom starts, so that's kind of the total inventory of nutrients that could be used for the coming winter's production period. And also Immigrant Sea, this is Jon's and yours series, and then in the Nordic seas, Norwegian Sea, they all just declined. And if you know that when it gets down to 2 micromolars, then this stops. This is actually quite a significant decline. I think it's much more important than just warming. Very often we hear climate change, oh, temperature, all the time. So one of my vendetta is that marine climate is more than temperature. And then you say safe. That one is also really hard to get. We have updated this, but not up to date. And so nice to contact people here at Havron, because you're it's nice to work with you guys, to see what happens to your system. And you recognize these stations, Faxaflow and Stocksiness. And we initiated similar measurements in the Faroes, and they show kind of the same trend. We had this decline, a slight increase after 2015. This was the convection period here, but not to the levels before. We are still much lower than before. So kind of rebounds, but not to the earlier levels. I have not, I don't know what happens right now, but I think we are somewhere in this average. Go to zooplankton. Calanus marschus, as you know, the main species in the subpolar North Atlantic. This is based on CPR data. They love to sleep down in wintertime in these big bodies of cold water. It's an oceanic species that needs to be brought onto the shells every spring and then to grow. And these are data from Selvågsbanche, which I bought from Astor Kristoffersson, part of this story. And you see really goes up and down, and this is total dry weight, and his has this main Calanus marschus. And this characteristics really resembles what we see on the Faroe shelf. That's why I emphasize on this spikiness. So when we have this gyre expanding, we also get more, or you should expect more Calanus towards you guys. And this story focused on this confluence of these Atlantic waters and these subarctic mode waters. In the Immigrant Sea, you have this strong frontal system that's very productive. You have the big redfish stock and fin whale concentration around this rim. This you all know much better than I do. Sometimes mackerel moving in there and maybe attracting bluefin tuna. So around the Immigrant Sea is very turbulent and active ocean. And here again, this is your Selvågsbanche, the black one, and you take the trend from this gyre index. This is based on a German model. Then actually, it's quite remarkable that when we have convection periods all these years, they all coincide with increased zooplankton. So from that work in 16 said increased zooplankton abundance when the subarctic front shifts towards Iceland or the subpolar gyre expands. And then another story. Now I want to start a home. I'll finish off in the Faroes. And the nice way to do it is with the birds, because these birds, many birds from Norway and the Faroes and Iceland, they actually occupy these waters during the non-breeding season. That's when they're not sitting on their nests. So that's most of their lifetime. In fall and winter and spring, they go to here and to Newfoundland, Labradorshire area, which means that the conditions around here are really crucial for the birds and their survival and their motivation to breed the next season. So the idea was they can simply fly the signals from here back to the Faroes. This was a story on the Kitty wakes. One important metric for the birds is called breeding success. It's how many chicks are fledged per nest. It's a very important metric for seabirds. And you see sometimes really bad and really high, so this on and off signal that we see also in the Faroes, which resembles these physical indices. Seabird people call this carryover effect. If they are stronger, they have more motivation to start breeding. So it carries over from the wintering regions. So that way, signals from here could actually be seen in seabirds directly in the Faroes. It could also be, as I mentioned, that open ocean things could influence onto a shelf, which I think it does in the South Iceland shelf. And we've been trying to look at oceanic influence onto the Faroe shelf. So this ocean shelf influence. And I'm getting close to the end now. 13. It's a belt, right? Isn't it? This is, we were looking from south, Atlantic inflows, but this is the gift from you to us. Or one of them. From the East Current, East Icelandic Current, there's lots of goodies in there, the big fatty Calamos finmarchicus and also Calamos hypoboreus. They come down towards us. And if you zoom in here, temperature down on 100 meters depth down here, Atlantic waters. This was actually one of the first studied oceanographic features by Helmer Hansen and Nansen 120 years from since. So we have these East Atlantic waters coming down here. We call this the Atlantic tongue, this protrusion of the tongue that comes to a variable degree into the southern part of the Norwegian Sea. And if you look at average zooplankton, the upper 200 meters north of this Iceland Faroe front, it is reddish. It's much more zooplankton. This is in May. For example, Calamos hypoboreus. They do extend down towards us, and also large stages of in May of Calamos finmarchicus. So now we also get this, both the subpolar gyre, but also from here, will influence the waters around the Faroes. Faroes, and this is the Faroe Channel, and we have, this is in April, lots of them just west of the Faroes, from where waters are flowing in and feeding small fish. They want, early in the season, they want to eat cobalt eggs and multi-egg. And then we have much data on cod and haddock and loricod and these species from where we derive indices. And this is an old schematic, but I just bring it in because it includes this Icelandic zooplankton, and I think it summarizes what I've been trying to say. We have the marine climate, gyre index. We actually have a primary production index on the Faroes that people have been using a lot. It goes up and down, local primary production. And in the midst of this, we have the Icelandic zooplankton. And measures measures of sample and other juvenile fish and the seabirds and also aspects of the cod and the demersal fish. And the synchrony really goes through the system. These colliers, they are seen all over. And I think it's interesting that to see there's some synchrony also to the South Iceland shelf. So we have so much to learn to look at our system and your system together, both from the Atlantic side and also from north and the Icelandic town. And this is something we work on. This is the last one. This is just a hypothesis we have worked on. Seabird paper that we have on our shelf and also your shelf. This really production spikes every 5 to 10 years. Really high production, recruitment to everybody. But then out we have some more slower signals, both from this gyre and also from here. And this hypothesis says that some of these spikes, like in the 90s, they went all through. I mean, caught and everything, had a great time. While the spikes in 2009 was one, and 2017, they were seen in small fish, but they were never really seen as adult caught. So that's really a conundrum what is bringing down the recruitment peaks. I would claim that we need both good production on the shelf, but we also need favorable conditions around the Faroes. So it's not enough to have really good spring bloom or summer bloom, because these small creatures, they have to grow throughout the winter. So things have to be favorable close to the Faroes, but also around us. And yeah, that's just my message. That's it.
Thank you, Hjálmar. That was a very insightful and interesting presentation. And without a doubt, we have many, many questions. Before we start, I want to tell the people online we can't hear them. They have to type questions in the chat, and then we will read them out loud. But Jón, please go ahead with the first question.
Thank you. Thank you very much for a very interesting presentation, Hjálmar. And thank you for being on the ground when you talk about Anna. And I think it's important to note that even if you are ground-based when you talk about Anna, and you're not alone, it does not mean that people that also are on the ground, they also, I think in general, are for reducing carbon dioxide emission. So, and there's no excuse for not doing that.
For so many reasons.
Yeah. I noticed that I just want to add to clarify how you explain the link between circulation and the concentration of nutrients in winter.
So the link between concentration in the winter time and production?
No, the link between nutrient concentration and the currents and circulation.
Oh, yeah.
The variation.
Yeah. And if, as you remember in our paper, one thing would be, it's the vertical, it's convection. I mean, if convection reduces, where is that one? It is here. So I think in one, there it comes up. Yeah. You said that when we have reduced convection, much of this is being brought up vertically. I mean, if you mix down to some years, maybe 1,000 meters, 700 meters, some years you mix down to 2,000 meters. So convection there will bring up lots more nutrients when we have periods with convection and then when the gyre expands. We did admit that this is the reduction in the nutrients is more linear than we can explain from the gyre index, for example. And this reduction, we cannot explain it all. We also discussed the trans-Arctic transport, I mean the Beaufort gyre, that sometimes retains, and much of the silicate that comes down this way does actually come from the Pacific. And many people claim that because the Pacific is much, much higher in the silicates. we claim that some could go, but there's so little data how much goes into the Labrador current. But I think we found that that will be just a small part of it. So we do not claim that we explain all of this reduction. And this reduction is also broader than just the North Atlantic, and it's almost global. There are many places that we have silicates decline.
I see. Yeah. So you basically link it to the variations in Labrador Sea process.
Yeah, convection. Yeah.
Okay.
And also in this gyre stuff, I mean, when this gyre is strong, there's more circulation that brings it back towards the Faroes. While if you open up here, you allow these blue waters to go through there. So also lateral.
Which is low in nutrients.
Very low in nutrients from the Bay of Biscay. So when you get those waters towards the Faroes, the nutrients will go down. So it's also convection. But we don't have the full. These are aspects I think that are involved. But it's not the full story.
Thank you.
Yeah.
Well, next question was Guðmundur, and then, okay. Guðmundur, please.
Thank you, Hjálmar. Very interesting topic as always.
Thanks.
I'm wondering, you talked us about the subpartial and what is happening there in the Labrador Sea, what gives this predictability power, what is happening further east, Iceland, Norwegian Sea. But I'm wondering, what is causing this variation in the subpartial? Is that atmospheric pressure, or what is it?
Yeah.
Can we predict anything about it?
Yeah, no, that's a tough one. I would say the principal driver is this one. And it's linked to the jet stream and the NAO, the North Atlantic Oscillation. And then you get up to the jet stream and things become much less predictable. Some people say or claim they could predict parts of the NAO from things in the Pacific linked to the ENSO system in the Pacific. But that's on the edge of where people know. But really, if you have, this is driven by really strong and really cold and dry winds from the Arctic, or from the Canadian Arctic. And to predict something like that, I don't think we can. So I think the prediction starts when we have realized really a strong winter with strong heat losses, and also what happened in the winter 2014 to 15 here. It was both the intensity of the heat loss, but it was also the duration. You had heat losses into May or so. It was a longer season also. And then this, after a period of no convection, boom, then it broke through again. But predictability up to into the jet stream is beyond my knowledge at least.
Okay. Move on to the next question. There are a few hands up. Theo, I think you were next.
Thanks a lot for the presentation. For me, it was very insightful. Many of these I didn't know them. So first, it's two small questions. First scale concerning this AMOC index that it has been used from Ramsdorf and other publications. Basically, while you're presenting this slide, you made an argument that's very interesting, that basically this index can be understood in the opposite completely way. So basically, I think that this is, I haven't seen it elsewhere, and I think that's a very interesting idea. So basically, my first skill of the question is, if you had, to initiate a study that would validate the assumption from these papers discussing the imminent collapse of the AMOC, where would you start, maybe based on this idea that you described now? And then the second one is a bit more generic, because I haven't worked with the AMOC. I have heard, people discussing about it, and I always feel that there is a distance on where the area focus is. So basically, people focusing on the North Atlantic Ocean, they're discussing about a reduction because we don't see an increase of the temperature there. We have the cold blocks. We see the rapid rise showing a reduction. But then if people are discussing about if they're focusing on the Nordic seas, then they probably don't see reduction in the transport over the Greenland-Scotland reach, and at the same time, there are questions about if there is a reduction in the overflow waters or not. So basically, people working in the north usually say that, well, guys, let's not get crazy about it, and then maybe people working in the south, they might be a bit more concerned because their data show something different. So I wonder if there is, how could we sort of maybe breach, this continuity there?
Yeah. And number one is down at Rapid. Do you know Rapid Array across the Atlantic? It's across from the Florida Straits, the Atlantic. They did claim, or do claim, that it has shown reduction. It's actually a fault. It's based on the telecable between the Bermuda or down there. When they have corrected for that telecable, there's no rapid, even does not show, so it's not observed decline down there either. The concept of an AMOC, it was actually Benjamin Franklin that saw it back in the days when he went to the States, that if you are further south, then it's clearly an AMOC system. It's warm in the surface goes north, it's cold down, so it's a very clear AMOC system. But as you move further north you get, the less important is the AMOC component of things, and the more important becomes the lateral, three-dimensional. So when you get into 50 or 60 degrees north, then the AMOC component has gone down, while the other lateral component goes up. So it depends on where you are. And this aspect that much of this cooling here is air-sea interaction, people have been writing about it, both in the Labrador Sea and also in the Irminger Sea. And people that really know these sites, they know that this is mostly heat loss to the atmosphere. It's not reduced lateral heat transports from the site, but it's heat loss this way. So there are papers on that part of the story. When it comes to how much goes past the Faroes into the Nordic seas, the paper by Ramsdorff and then his followers, they say, oh, we have the cold blob, and they focus actually on the subpolar gyre itself and find a cold blob, but it's actually different in the Nordic seas for them. And they write in their nature paper, oh, that's beyond that's maybe not a part of the AMOC, they claim even, or that's beyond the focus of our study. So that's also what I mean about is it well defined, because these guys do not even count the transports past the Faroes as a part of the AMOC. So how well defined is it? I mean, for us, that is the AMOC. So it depends on who you ask, even the experts. So how should the lay people be able to understand this feature? These people and us are still disagreeing. So if you read their paper, it's actually a different signature over the subpolar gyre and then the Nordic seas. So that's why I claim that the concept is not well defined.
Okay, let's move on to.
Is that something? You had a question?
Yeah.
Yeah. Thank you very much, Hjálmar. Now that you are here on this one, like you mentioned something about memory. Isn't that memory the stratification? So that's the precondition of the water that you have. So the water, I could see like when there's not a lot of color, then stratification is basically zero. And that means that it's very easy to lose all the heat and just create gigantic convection. Like I think this area has the record 3 kilometers mixed layer depth. So that's like, but it's because the water was preconditioned.
Yeah.
It's like, it has a stratification that it just was modulated. And those are the things that variables that we are looking into is this sort of stratification. Is it changing with time? That's another key process of the story. And I think that one is very important. But it's linked to this one. So you have the Labrador Sea water, and when you show your blocking mechanisms of the subpolar gyre, like maybe I know that it's a cartoon, but it seems that the subpolar gyre increasing in size, it blocks North Atlantic water or the Atlantic water. And you mentioned that there's a current that pushes this water, that is Labrador Sea water. Which current is pushing that water? Because we don't have that current in the schematics that we have.
No. I'll show both. First, your first question is about stratification and preconditioning and memory. What actually happened here in the Labrador Sea was the winter 13 to 14, it started to really start to convect down there already at that time. So then the Labrador Sea started to precondition the system. And then if you follow the next winter, it's also strong heat losses. Then the water column was already unstable, fairly homogeneous, and that's the memory of the system. Some people call it re-emergence of these signals because they're capped off by warm water in the summertime, but still it's homogeneous down below. When the next winter comes, it's easier to break through a more homogeneous layer. And if that winter also has a massive heat loss, as the winter 2014-15 had, then it goes all the way. And that occurred, then you got convection even in the emergency. All this period, but first here you broke all the way through. Yeah, you see here, this first one here, this winter here, this preconditioned down there in the Labrador Sea, those waters that do flow towards the Irminger Sea laterally. So then you get this water column flowing into the Irminger Sea. And it's fairly homogeneous. And then this winter here, 2015, it happened again. And then you see convection all the way down. And the currents that are going this way, did I show? Yeah, something like this. From here, when you have convection here, these deep waters that do flow along the Reykjanes Ridge around there, this way, at depth, Labrador Sea water. And also the Irminger Sea gyre goes around here, and also when the gyre becomes stronger, then at depth, waters are also pressing north through the Iceland basin, and the extension of this limb, how far north towards Iceland it comes, that varies a lot.
So which current, does it have a name, that current?
No, I don't think so. It is. It's an advection of slow, I mean, subarctic waters, Labrador Sea water, it goes slow down there. I don't think it has actually a name. It does also go into the Rockall Trough. So it's kind of slow advection of waters.
But is it affected with the Atlantic current?
No, this has been part of it.
Not with the modified Atlantic currents?
No, this is the body of the subpolar gyre itself down at the kilometer depth.
Okay.
Yeah. So that kind of is three-dimensional and lies underneath, and then the valley flows lighter. So I don't think this is just advection. When this is really collecting here, it goes at depth slowly towards us.
Okay.
Yeah.
So next we are going to take one question online that is in the chat because we cannot hear the people online. So I'm just going to read it out loud.
Yeah.
And it's from Sigurður. And he says, thank you for a great presentation of your interesting research. In a much-cited paper on climate nonlinearity, Lenton et al. 2008, presented the Atlantic thermocline circulation as a tipping element, saying that circulations clearly pass a THC tipping point this century. What is the relationship between THC and AMOG, and do you think these simulations also use a flawed proxy?
THC and the tipping point, I think it came from Stommel back in the days, American really famous oceanographer. We made box models up here. From that very simple calculation, he says this system can tip into different states. Okay, so very simple, just this is one box and this is another box, and then you allow fluxes between them, and there's a math you can show these tipping points that many people talk about today. Yeah? Mm-hmm. Then in the 90s or in the 2000s, people were talking about the THC, it's the thermohaline circulation. And we talked about also the thermohaline, I don't know if you can hear me, thermohaline circulation, from the idea that it's only cooling and convection, this havsins kalda hjarta, that Boy Hans used to call it, the cold heart of the ocean. that means that the engine of the conveyor is actually here. It is cooling, becomes denser, thermohaline is thermal temperature haline is salinity, so temperature salinity into density, so it's density driven. And then you had Ferrari and many others around the world oceans that say, no, it's not the engine is here, it's further south, it's to bring all those cold waters from depth around the world oceans back up again. That's internal tides and mixing, all that mixing, that's where the energy from the moon actually. So now it's kind of a chicken and egg question. Where is the engine that drives this conveyor, if there's a conveyor? So then people in the early 2000s or so slowly went away from the concept of the THC, because that's density driven, to something is overturned. Whether it's driven by mixing in the world oceans or if it's driven by density up north, it's still overturning. So to get away from that discussion, you go into the MOC, where it's all overturning, and then you have the Atlantic meridional. So then people went over from the THC to the MOC.
That was very interesting. There are no more questions online, but there are more hands. Great, please go ahead.
Yeah, my question is on the infragravity waves. If you add kind of topography to those blue streams, can you kind of generate map of internal gravity waves?
That is beyond my knowledge. I mean, these streams are really slow. It takes maybe 1.5 years to go from here to here. So I know too little about internal gravity waves. That's more you guys, your field. We had this nice chat this morning about those small scale features. I would say not those, but if you have this overflow that goes through the Fairbank channel and comes this way, that's fast. That's a really powerful, and all kinds of waves are there. You can see it when we're out in acoustics, all the waviness, it just shivers all the time. So I would say these are slow, but demonstrate, and the Fairbank channel and the Iceland Faroe, those, they will initiate gravities.
Okay, one more question. Please, Peter.
Okay, thank you. Just moving back into the drama.
Yes.
I'm just wondering if you could clarify. Maybe it was spoken about a little bit earlier, like they speak so much about the tipping points of the AMOC, and we might even have passed it, and so on and so forth. Like, is this concept of a tipping point? Do you think it makes sense, like whether we could like test it or not, or whether it's happening or not? But yeah, is it this dramatic?
I think it. I think it came from the Stommel.
Sorry,
the Stommel,
oh.
this famous guy that made these very, very simplified box models, very simplified model of the reality. And from that, he came to these different states. Sometimes you have deep convection down there, sometimes you do not. So you have more than one state at least. And then this concept of a tipping point, I kind of recited in the system all the time. It has been rejuvenated now recently. I don't think, I hope not, that this system can really plunge suddenly like that again. So I think it's very impactful, like this paper by Ditlevsen that were totally viral this summer. Last year. I had this presentation of part of it in Greenland a month ago, because he was just presenting after me. Because he takes on this one and then he goes directly into statistics and all kind of hysteresis. That's one paper. Another one is by another group down in Holland. I forgot the name of them. We have taken big models and you are bending their arms so far that they eventually break up, saying that you are pressing, they call it the hosing experiments in these models, where you let a lot of fresh water into the systems. And when do they actually show a stop? What's his name? No, from Holland.
Utrecht University.
Yeah, I think so. What they did, they let Greenland melt 80 times the daily rate for many years. So, I mean, how realistic is that? And after a while, boom, there's tipping points. And then they go into nature and world media, and far down, by the way, we let Greenland melt 80 times the present rate. So if you really want the models to shut down, you can do it, but not in a very realistic way. And then people say, oh, it did shut down, and even, unfortunately, also people in Paris, it came in the media, that, like Ditlerson says that the year 2000 and something, 40 or something, this is gonna happen. So when you put a date to it, that's very effectful, because now people can relate to it. So many oceanographers, we feel that it's, I think somebody called it the dual ethical bind of us, because we need to promote this discussion, because we need the world to understand that we need to get the CO2 down for so many reasons. There's no doubt about it. But maybe to overemphasize a bit too much, when you do this tipping, and this is actually going to happen now, you get a reaction. And then we are thinking like activists or whatever. It could maybe be defense, but the dual ethical bind is that we also have to be fair to science. I think that's more important. So when we say, oh, according to Ditlerson, then the year 2014, 40, this is going to shut down, and then it's going to be 10 degrees cold in the Faroes in 20 years' time. I mean, when you say something like that to the media, people get scared, and they say, oh, it's warming the ocean, but it's really cold. I mean, we are confusing people now. And now we are kind of going into, we shouldn't do that, with Ramsdorf going one way, and the other should go and have the discussion in the media, that everybody's going to be confused. So I think Ramsdorf and all of us could go in a big hall, boxing gloves on, and take the fight in there, and then come out when we have white and something like that, to get a consensus somehow.
May I add to this? I mean, what you're saying makes sense that, all right, if we want to motivate people, we could potentially, some people might argue that we could, over-dramatize, a situation, but what is happening is, I think, the opposite, because we're reaching the point where it doesn't even matter what we're going to do, because the EMOC will collapse. We have passed the tipping point, as Stefan Remsdorf claimed when he was doing his presentation here in Iceland.
He did? What was that?
Before a month, about
really?
some weeks, and most likely we crossed the tipping point, or at least it is very likely.
Did you hear that?
Yes. Yeah.
Dramatic.
It was on this Nordic countries.
Yeah.
So where I also presented these
The
results to the politicians.
His letter.
Yes.
Signed by many people, without saying how many people were invited that did not sign this one. That is much longer.
Yes, we have to present the data correctly.
Yeah, and that's also it. I mean, if we go out and cry wolf loudly, say we are the bad word, we are then there's no need to do anything. You can be apathetic and lay down. We're dead anyway. Yeah? So people just don't care. I mean, we risk to get also polarization. I know many people are saying get your grit together, and they start to lose faith in science. And then we have some really pro people who just increase the divide or the kind between us. That's why let's take it down so we can trust each other.
That's a very good point, very good take-home message. And any more hands? One more question, or are we all done? We had a very interesting half-an-hour discussion. It's been excellent, Hjálmar. And a pure pleasure listening to you. And Hjálmar is actually here for 3 more days. So you have to come up with more questions. No, he's actually here in the house for a meeting for the next 3 days. So you're going to see him during the coffee break and lunch break. So if you have more questions later, don't be shy to go and talk to him. He's a very chatty, friendly guy, as you've seen. Yeah, make sure he has enough food, then he's definitely nice. But yeah. You don't want to talk to him when he's starving, just leave him alone right then. I know that by experience. Well, thank you all for being here today. It's been a pleasure to see how many people came, and have a wonderful day.